So good morning to everyone. Good morning. Okay. So today we have regular this one class, not related to CT and NEET, right? I think some of you have attended CT, NEET, that's why I am telling this one. Anyway, so we are going to start with the solid state, which we have already initiated. Right? So that's where we have the solid state. Fine. Now when it comes to solid state, what and all we have discussed? 3 days back or 3 to 4 days back it was. What and all we have discussed with respect to solid state. So we have discussed about types of solids. That is related to, and one is crystalline solid. One is crystalline solid and another one is amorphous solid. Amorphous solid. Now amorphous solid can also be called as pseudo solids or amorphous solids can also be called as pseudo solids or supercooled liquids. Supercooled liquids. These are the different name. Supercooled liquids. Now that's what I will talk about. Two important words which we have discussed. One is long range order with respect to crystalline solids, right? When it comes to amorphous, it was short range order. It is short range order. When it comes to crystalline, it is long range order. But when it comes to amorphous, it will be short range order. Right? So that is based on the arrangement of the elements in the crystal. So that's where we have the long range order and short range order. Then another important property is one is anisotropic in nature. Crystalline solids are anisotropic, but here it will be isotropic. Right? So that's where when light rays are passed at different angles, or when the light rays will incident on the crystal at different angles, they have the different types of diffraction and all. That's why it is called as anisotropic. But when it comes to amorphous, that is not there. Therefore, it is called as isotropic. Whatever the angle of incident, it will be same. Property of radiation or bending of light will be same. That's where we have the isotropic. That's what I am telling about refractive index, right? So that's where we have the crystalline and amorphous solids. You have to remember these terms, whatever I have written on the board. Now, along with this, when it comes to crystalline solids, once again it can be classified as, crystalline solid can be classified as, first one as molecular solids, right? First one as molecular solids. So in case of the molecular solids, once again we had non-polar, then we had polar, then hydrogen bonded molecular solids. So in the name itself it is there, molecules. Molecules are the one individual entity which are involved in the formation of the crystal structure. So therefore they are called as molecular solids. Now based on that we have non-polar, polar and hydrogen bond. So that is one of the crystalline solid. Then we have discussed about ionic solids. Then we have discussed about ionic solids. Okay, manganese oxide, someone had asked, right? So manganese oxide, it will be somewhere around 535 degrees Celsius. 535. Someone had asked, right? Manganese oxide. So ionic solid where melting point will be 535. So what I mean to tell here is, when it comes to molecular solids, low melting point, or I can tell very low melting point. Okay. So most of them it will be below 0 degree Celsius or maximum 0 degree Celsius. That's how you can remember. When it comes to ionic solids, it will be less than 1000 degree Celsius. I am not telling universal, but most of them they will be having melting point less than 1000 degree Celsius, not 100, 1000. Now, next one we have discussed about metallic solids. Metallic solids, where normally it will be greater than 1000 degrees Celsius. Ionic solids, it will be less than 1000 degrees Celsius. But when it comes to metallic solids, it will be greater than 1000 degrees Celsius. And we know metallic solids, they are malleable and ductile due to the presence of metallic bond. So what do you mean by metallic bond? So this is the interaction of a electron of one atom with the another nucleus of another atom. So that's why it will lead to the formation of metallic bond. And due to the presence of free or loosely bound electrons, they are thermal and especially electric conductors. Right? They are thermal and especially electric conductors. Which one? Metallic solids. And all the other solids, they are non-conductors of electricity. Right? But when it comes to ionic solid, when it will get melted or fused form, definitely it will be a very good conductors of electricity due to the formation of free ions, due to the availability of free ions, only when it is melted or fused condition. But whereas a crystal, no, it is a non-conductor of electricity because non-availability of free ions, due to the non-availability of free ions. And another important property with respect to ionic solid is they are brittle in nature. And I told what is the reason why they are brittle in nature. Fine. So that's what we have discussed in the last class. Now we are going to discuss about covalent solids. Last category which belongs to crystalline solid, a type of crystalline solid. That's where we have the covalent bonds which are present between the individual elements in the crystal. So which is that interaction? It is the covalent bond. In all the other cases, either it will be non-covalent interaction, or it can be metallic bond, or it can be ionic interaction, right? So yes, Jannavi, diamond and graphites, they are very good example for covalent solids. Graphite and diamond, they are the very good examples. And one mark question you can expect on this. First PUC already people have studied in allotropes of carbon, and once again in second PUC also it is there. Now when it comes to graphite, it is having layered structure. Right? So what I mean to tell you is, this is one layer, this is another layer, this is another layer. In each layer, carbon will be interacting with three other carbons, neighboring carbon. In each layer, a carbon will be interacting with three other neighboring carbon. And that's how they are arranged layer-wise. Now if I observe, I told carbon is having or interacting with three neighboring carbon. Right? I never told four. So that means graphite should show sp2 hybridization. Right? So that's where we have the graphite sp2. Right? Now, when it comes to graphite, due to the formation of layered structure, it can be slippery. One layer can slip over the another layer. So, due to this property, it will be used as a lubricant. Due to this property, it will be used as a lubricant. Right? So, all of us we know, whenever we will give our vehicle for servicing or cycle, they will apply grease. So what is the role of grease? It will act as a lubricant. So that's where it will be used as a lubricant for smooth functioning of these machines. Right? That's where we have the graphite. Now why it will be acting as a lubricant? Because due to the presence of layered structure. Okay? So which is the hybridization? sp2 hybridization. Now, very important point here is, sir, carbon is having total 4 valence electron, but you are talking about only 3 bonds. What will happen to another electron? So that's where we have each layer where we have the electrons which are freely available. In each layer we have the freely available electrons, and due to the availability of the electrons, they are good electric conductors. They are very good electric conductors. So that's where we have the graphite. Whether I am clear? So graphite is having sp2 hybridization. It is having layered structure. So due to that it will act as a lubricant. And due to the presence of sp2 hybridization, but there is no double bond, it is a single bond. So due to that there will be availability of free electrons. So now, because of which graphite is a good electric conductor, we should remember this. Now when it comes to diamond, it does not have the layered structure, right? So it is a very hard crystal. It will form a very hard crystal. Now naturally it cannot be used as a lubricant. So that's quite natural. We cannot use it as a lubricant because it is a hard material. Right? So now, why diamond is very hard in nature? That is because it is having sp3 hybridization. Due to the presence of sp3 hybridization. Sir, hagadre methane CH4 is also having sp3 hybridization. In that case, why methane they are liquid at room temperature? Why they are not present as a crystal? That is because of intermolecular interaction. When it comes to methane, where each methane will be interacted with another methane by the non-polar interaction, a weak interaction. But when it comes to diamond, whatever carbon sp3 hybridization is there, each carbon is interacting with another carbon. So carbon-carbon interaction is there. There is no other element. It's only the carbon. So due to that, diamond is the hardest material, right? So it is formed hard crystal, and there will be presence of sp3. Naturally, there is no question of free electrons. So due to that, they are non-conductors. Non-conductors of electricity. Unlike graphite. These are some of the important difference between diamond and graphite. These are some of the important differences between diamond and graphite. Okay? Now, when it comes to melting point, don't think that graphite, since it is soft material, don't think that it is having low melting point. No. If you see the melting point of graphite, it is approximately 3600 degrees Celsius. Can you imagine? It is approximately 3600 degrees Celsius. Very, very high melting point. If I go with the diamond, it is somewhere around 4000 degrees Celsius. If I go with the diamond, it is somewhere around 4000 degrees Celsius. Very, very high temperature. See, when I am talking about ice, a molecular solid, hydrogen bonded molecular solid. So when it comes to the ice, its melting point is somewhere around 0 degrees Celsius. Right? If I take NaCl, its melting point is somewhere around 800 degrees Celsius. If I talk about another ionic compound, that is manganese oxide, MnO2, its melting point is somewhere around 535 degrees Celsius. If I take iron, its melting point is somewhere around 2000 degrees Celsius. But when it comes to graphite, diamond and all, the temperature is somewhere around 3600 and 4000 degrees Celsius. That shows that covalent bond is a strong interaction. Covalent bond is a strong interaction. All of you will agree? So same way, any covalent solids if you take, they will be having very high temperature. For example, if we have silicon carbide, so which will be used in brakes, clutches and all. Why it will be used there? Because it's a very strong crystal, hard material, not as diamond but still it will be hard material. Melting point will be somewhere around approximately, I am telling, 2500 degrees Celsius. So I am talking about 2000 only, nothing below 2000. And in this case it is even above 3000. So that shows that among the solids, among the crystalline solids, covalent solids are the one which will be having very, very high melting point. Then comes the metallic solids. Then comes the ionic solids. And when it comes to molecular solids, they are the one which will be having low melting point. They are the one which will be having low melting point. All of you have understood? Any doubts? So in that case, shall I move to the next one? Next concept. Now, when it comes to crystalline solids, we have a term called as crystal lattice. We have a term called as crystal lattice. Now, lattice is regular term. Lattice is nothing but a mesh type of structure. Lattice is nothing but a mesh which will be used as a filtering agent. At your home, your mother will be preparing tea, right? So whenever she will be preparing decoction and all, they will be using some saucer type, right? So that will act as a mesh. So that is nothing but lattice. Why they are called as lattice? Because if I want to show the three-dimensional, whatever I am showing here, it is actually 2D. Imagine that same thing is on the back side of the board also. So if you observe this one, this is an example for crystal lattice, where I can tell that each point where two lines are meeting, each point we will consider it as lattice point. Each point we will consider it as a lattice point. And these lattice points are interacting with bonds. That lines indicates the bondings present between these lattice points. Hagadre, what are these lattice points? Lattice points are nothing but it can be molecules or atoms involved in that crystal structure. Sir, why covalent solids are called as network solids? Okay, Prajwal. So when it comes to covalent solid, if you observe, we have carbon, like that. Same type of element is having networking. What do you mean by network? Network means interacting with neighboring, like that it will goes on. And all of us we know carbon is having a catenation property. So due to that it can show the networking character. Right? So it's not a linear type of structure. There will be branch, there will be interacting with different carbons. So therefore it is called as network solids. Whether I am clear? Therefore it is called as a network solids. Any doubts? Okay? Because in all the three-dimensional view, they are forming the covalent bonds. And that covalent bond is not restricted for one piece one. It is spreading. See, for example, when I am talking about methane, here also covalent bond, but it is restricted to methane only. One molecule of methane. If I take another methane, they are not forming covalent bonds with each other. Right? So they will be having non-polar interaction. But here, all of them, they are linked by the covalent bonds. So therefore, covalent solids are called as network solids. Yes, it is called as network solids. I forgot to tell that one. Okay, na? Now we got the answer, Prajwal. Okay, so therefore they are called as network solids. Whether I am clear? So now I will come back to crystal lattice. Now crystal lattice is nothing but a three-dimensional arrangement. It's a representation. It's a three-dimensional arrangement of the unit cells. Or I can tell unit cell we have not told. Na? So it is the three-dimensional arrangement of the elements in a crystal structure. That will be represented by crystal lattice, or you can tell that crystal lattice is the representation of the three-dimensional arrangement of the, it is the representation for the three-dimensional arrangement of the elements of a crystalline structure, elements of a crystalline solid. Fine, that's why it is called as crystal lattice. And each element, which can be molecule or atom, each element they will be considered as lattice points. It will be considered as lattice points. So therefore, what are lattice point? So lattice point is a representation in a crystalline structure, or it is a representation of an element or molecule in a crystal lattice. Okay, so that intersecting of those lines, that is called as lattice points. So lattice points are nothing but a molecule or an atom. Whether I am clear? So that's where we have the crystal lattice. Any doubt? Crystal doubts idya? So that's where we have the crystal lattice, which is a three-dimensional arrangement of the element in a crystal structure. It's a representation. Lattice point is a representation for the crystal structure. Fine? Hagadre, we have another important term that is called as unit cells. That is called as unit cells. Now, when I am talking about the unit cells, it is the smallest part of the crystal lattice. It is the smallest structural unit of the crystal lattice. Right? Smallest structural unit. Smallest structural unit of the crystal lattice. That's why it is called as unit cells. How it will be like a brick. Each brick will come together to form a house or a building, right? So those type of individual bricks are considered as unit cells, and that whole building will be considered as a crystal lattice. So that's where we have the unit cells. Fine? How to represent these unit cells? So we can represent the unit cells where, okay, so this is a unit cell. It's a cube. It's a cube which is there in your syllabus. Don't worry. It's a cube. Now if you observe it carefully, what is the speciality of the cube? Where everything will be constant. A. Right? So all the edges of equal length. That's why it is called as cube. But it can be variable. I told this is one type of unit cell. This is not the only unit cell. It is one type of unit cell where all the edge lengths are constant. I have represented. Right? Now same way, there will be presence of the angles. at this particular point, right? Or I can show it here, 1, 2, 3. So this is one angle, this is one angle, this is one. I will represent it as alpha, beta, gamma. So they are called as edge angles. They are called as edge angles. So we can represent the unit cell like this, or we can have different types of unit cells. Different types of unit cells which will be decided by, one is edge length. One is edge length. It's not compulsory that edge length should be same. It can be vary. Okay? So that's where edge length is one of the things which is going to decide. And another one which is going to decide is alpha, beta, gamma. Angle value. Edge angle value is going to decide which type of, or what is the shape of the unit cell. So therefore, shape of the unit cell, that is types of unit cells, can be decided by, one is edge length and another one is alpha, beta, gamma. So like that, based on this we have total 14 types. We have total 14 types, 14 types of unit cells. And based on that we can have the different shapes of the crystal structure. So 14 types of unit cells are there, which will lead to the formation of Bravais lattice. Person name who gave this idea, Bravais lattice. Okay, so based on the edge length and based on the alpha, beta, gamma, that is edge angle, so we can have total 14 types of unit cells which can lead to different form of crystal structure, and all together it will be called as Bravais lattice. So what is Bravais lattice? It is the representation of different types of unit cells due to difference in their edge length and edge angle. Okay, so that's where we have the Bravais lattice. Whether I am clear? All of you have understood? So this is where we have the crystal lattice and unit cells. That's what we have discussed now. Crystal lattice and unit cells. What do you mean by crystal lattice? Crystal lattice is nothing but a three-dimensional arrangement. It is a representation of three-dimensional arrangement of elements in a crystal structure or in a crystal lattice. That is nothing but crystal lattice. What do you mean by unit cells? Unit cells are the smallest structural unit of that particular crystal lattice. So crystal lattice is a broad term, unit cell is a small term. Like in an apartment, the whole apartment is considered as crystal lattice, and individual house, it will be considered as a unit cell. So that's where we have the relation between crystal lattice and unit cells. Okay? Now whatever I will be going to tell, it is very important. It is very important for your exam point of view. Now when it comes to types of unit cells, covalent solids and molecular solids, here and there once in a while they have asked. And with respect to pseudo solids and crystalline solids, they have asked 1 marks here and there. But here it's bit important. There you can mention it as important, that's all. Here it will be very important. That means once again I am talking about types of unit cells. But that is not based on the shape. Whatever I will be telling now, that is not based on the shape. Okay? Now, when I am talking about types of unit cells, so we have one as primitive unit cells. Okay? And another one as centered unit cells. Centered unit cells. We have primitive and another one as centered unit cells. Hagadre, when I am talking about primitive unit cell, we can represent the primitive unit cell like this. Okay? We can represent where we have the atoms. In reality, these atoms should touch each other. If I do like that, it will not be clear. That's why I have shown it a bit far. So that's where we have the primitive unit cells. In centered unit cell, once again we have three types. Okay? So one as body centered. And another one as face centered. And the last one is edge centered. So we have three types. If I want to represent body centered, I can write like this. Okay? So corner atoms, there will be presence of corner atoms. Along with that, there will be presence of atom in the center of the cube. So what I mean to tell here, if you take a box, anything, it can be a TV box or it should be a cube type, that's all. If you take TV nowadays, it's coming flat screen, that is different. Old one if I take, or you can take any box, a cube. If you could put a cricket ball inside that one, right? So that will be considered as this one, blue colored. That is nothing but blue colored element or atom. Fine? So that's where we have the body center. Therefore it is called as body center, because in the center of the cube we have a atom. Okay? Now when it comes to face center, where we will be having atoms present in the corner. But along with that, there will be presence of atoms on each face of the cube. Okay? So don't get confused. A cube will be having how many faces? Imagine this one as a cube. It's not actually a cube, but you should imagine. Now, I have 1, 2, 3, 4, 5, 6, 7, 8. It is having 8 corners. Yes, Samit, you are right. So it is having 8 corners. Right? So whichever atoms they are present in the corners, they are called as corner atoms or corner elements. Okay? Now, anything which is present on the face, this is one face, this is another face. So this is another face, like that, here one and here one. So this particular box is having how many faces? 6 faces. So 1, 2, 3, 4, 5 and 6. So total 6 faces. Same logic is applicable there also. Now along with the corner atoms in the face center, along with the corner atoms, on each face there will be presence of the atoms or elements. That's what they are called as face centered. Okay? Now when it comes to edge center, if you are not understanding, you should tell me. Okay, this is a cube. So corner atoms will be there, no doubt. There will be presence of corner atoms. Now, any of the two opposite face, they will be having atom at the center of the face. Any two opposite face, not all the 6 face. Any two opposite face, they will be having atoms on the face. See, for example, if I take this box, either this face and this face should go in combination, or this face this phase should go in combination. So any of the two opposite phase, they should have the atoms in the center of the phase. Then they are called as edge center. Then they are called as edge center. So what I mean to tell here is, when it comes to primitive or centered unit cell, what is that common in all these? In all this, there will be presence of corner atoms. It's common. Here also corner atom. In all these three, we have the corner atoms. That is the common feature. Right? Now, what is that difference? So, difference here is, in primitive unit cell, we have only corner atoms. Nothing else. Right? We have only corner atoms. Yes, Amit. In all of them, they have the atoms at the corners. Right? But when it comes to centered unit cells, now there will be presence of additional elements. It can be atom or molecule. Additional elements will be present along with the corner atoms. So therefore they are called as centered unit cell. Because already corners are filled. So what is left over? Left over will be either center of the face or center of the cube. So therefore they are called as centered unit cell. So in case of the body centered, corner atom and one atom in the center of the cube. In case of the face centered, all the corner atoms and atoms on the face of the center of the each face. And when it comes to edge centered, we have corner atoms along with that at the center of any two opposite face. All of you have understood? You have to understand this, because very important one is not related to this, means not this one. Very important one is next one. 2 marks question they will ask. Calculation of number of atoms in a unit cell in a crystalline structure. That's what they will ask. That is for 2 marks. That's what it is important, very important. But if you have understood this one, then only you can follow that. Otherwise, you cannot. Fine? So that's where we have the primitive, body centered, face centered and edge centered unit cells. Okay na? Fine. Now we will come to the point. Very important one is whatever I will be talking now. That is calculating the number of atoms or molecules, whatever it is. Number of atoms in a unit cell of a crystal lattice. Please try to understand this sentence. I never told calculating the number of atoms in a unit cell. That's quite easy. Right? In a corner atom it will be total 8. In a primitive unit cell it will be total 8. Body centered it will be 8 plus 1, 9. Then in case of the face centered it will be 8 plus 6, 14. And in case of the edge centered it will be 10, 8 plus 2. That is for a unit cell. But I am telling that calculating the number of atoms in a unit cell of a crystal lattice. I am not talking about one unit cell. I am talking about unit cell present in a crystal lattice or crystal structure, right? So if you go to city, we have the multi-complexes, right? Where multi-floor storage buildings will be there. So same logic is applicable. See, for example, I have one unit cell. I am poor in the drawing, so you should not laugh. Until here, that's fine. But now, another cube also we should show, neighboring cube. So another neighboring cube can be, I can show it here. Okay. So I will make this one to join. Okay. Now here also they can join. Okay. So how many shops are there now? 3, right? So total we have 3 shops. So 1, 2, 3. 3 shops are there. Whether you can see in that one? I think it's clear. So we have the 3 shops, right? So we have green color, right? 1 minute. Okay, I will make this one as green color so that you can understand easily. Okay. So we have the 3 shops. One is in black, one is in blue, and another one is in green color. Now you should imagine this is one level of structure in a crystal lattice. It is one level of structure in a crystal lattice. Same thing will be there on the top, same thing will be there on the bottom, same thing will continue on this side, and same thing will continue on the other side. All of you will agree? All of you are understanding? That's what we can say here. Now, if I take a primitive unit cell, that's where we have the corner atoms. So 1, 2, 3, 4, 5, 6, 7, 8. So this is a primitive unit cell. Imagine it is a primitive. All of them they are primitive, but I have represented only. I have showed in only in center one. It is a primitive unit cell. Now you should tell me. This one, this corner atom at present, how many unit cells are sharing this particular corner atom? Only in this you can tell. Now at present I have 3 unit cells I have represented, right? Now just tell me that this particular atom is shared by how many unit cells? I want the answer. Whatever diagram I have shown in the board, according to that, each corner unit cell will be shared by how many unit cells? Anyone? Okay, someone has given. Okay, Kritik, very good. At present, as we have seen the picture, each corner atoms are shared by 2 unit cells. Purnima, that's why I told, go with whatever I have written on the board. Fine? So it is shared by 2 unit cells. Now imagine, now start imagining. Now we have another unit cell above this, and we have another unit cell above this. Listen to me carefully. Now we have 2 unit cells. Now imagine that above this unit cell another one is there. Above this unit cell another unit cell is there. If that is the case, each corner atoms are shared by how many unit cells? Whether you are getting my question? So according to this picture, yes, these atoms are shared by 2 unit cells. That is fine, one story. Now imagine that same layer of unit cell is present above here also. So one is above this unit cell, another one will be above this unit cell. We have another one. Yes, Amit, very good. So now it will be shared by, okay, all of you are giving the answer. Very good. That is 4 unit cells. So that is 1, 2, 3 and 4. Whatever I am showing here, 3 and 4, that is your imagination. Therefore I told in the beginning, solid state you should be having that imagination. But if you are not understanding, let me know. So this is 1 unit cell, this is 1 unit cell. In the beginning, these atoms are shared by, if I take this atom, if I focus only on this atom, then I can tell that this unit cell is also having this atom, this unit cell is also having this atom. It is shared. Right? It's like in a building, a corner of a room, it will be shared by 2 more rooms, if at all neighboring room is there. Same logic. Since these edges are shared by these two. These edges, they are shared by these two unit cells. Naturally, atoms present on those corners, it will be at present, it will be shared by these two unit cells. Clear? Now the question was, imagine that above this unit cell another one is there, and above this unit cell another one is there. Now same thing, this will be the corner for even those unit cells also. For example, here that's where we have the one side, only one side I am showing, okay, and same logic is applicable here also. This is the another unit cell which is present above these two. Now I can see 1, 2, 3, 4. 4 unit cells are involved. 4 unit cells are involved. All of you are understanding? Any doubts? 4 unit cells are involved. Now imagine same set of 4 is present on the other side. Same set of 4, it will be present on the back side, which I cannot show here. Same set of 4, it will be present on the other side also, because this corner can be a corner for this room, the room present over here, the room present over here, and same way this will be the corner for the room which is behind this, a room which is behind this, a room which is behind this, a room which is behind this. Right? So all of you are understanding? If you are not understanding, I am ready to explain it once again. All of you are understanding? So that's where, now can you tell me, this one atom, if you focus on this one atom, how many unit cells they are going to share? Oh, Bharat, very good. Okay, all of you agree? So that means this one corner atom, since we are focusing on this one corner atom, it is shared by 8 unit cells. This is the reason each corner atom, it will be shared by 8 unit cells altogether. Okay? Now, calculating the number of atoms in a unit cell means it's like we have one dosa. Okay? Raghavendra sir is having one dosa. Now total 8 students approached to Raghavendra sir. And now for Raghavendra sir all students are same. He cannot discriminate among the students. Oh, he is first rank, he is second rank, she is having low marks in chemistry. So no discrimination. So what he will do is, he will make this dosa into equal piece. How many pieces he has to make? He has to make total 8 pieces. If it is wrong, here whatever drawing is there, don't scold me. So imagine that here it looks like it is of larger size. So don't think that one. Imagine that Raghavendra sir has made it to 8 equal pieces, and each piece has been distributed to, okay, Purnima, you got it out. Okay, fine. Now imagine that, I will try to draw the picture, but it should not spoil the okay. Upper house is ready. It looks same way. Here also I can draw. Another house is also ready. Now Purnima, observe here carefully. Instead of taking this atom, I will take this one, which you can focus here. Now if you observe here this corner atom, whatever I will be talking about this corner atom, same thing will be applicable for all the 8 corner atoms. Okay? Now imagine that we have one corner atoms, right? So at present it is shared by 1, 2, 3, 4. Total 4 unit cells it is getting shared. So 1, 2, 3, 4, total 4. Right? But same way, this corner atom will also shared by these 4 units or whatever it is. That same thing is present on the front. Same thing it will be present on the front side also. Right? Same 4 types of unit cells, they are present on the front also. Or imagine you are constructing a house. What we have done is we have made 3 lines of shops, and above that we have 2 shops, and now you are planning to go for another rows of shop in the front also. Right? So if that is the case, 1, 2, 3, 4 and front 4. Total how much? 8. So that means this corner will be common for all those 8 rooms or all those 8 shops. Now you got the point, Purnima? Not 6. The 6 cannot be coming. It should be 8. Imagine, or you can see the corner of your room where you are sitting. You can see the corner of the room. Imagine that corner as one unit cell, and that corner will be shared by 4 rooms of this floor and 4 rooms of top floor. So total how many rooms? 8 happened, right? So that's what I mean to tell. Okay, fine. In that case, that's what corner atoms will be shared by 8 unit cells. Fine. So therefore, when it comes to calculating, the picture is not required. In your exam, if they ask, calculate the number of atoms present in a primitive unit cell, no pictures are required. To make understand, I have written these things. It's not required. It's only for 2 marks. So what you can do is, primitive unit cells, I am talking about primitive unit cells. Primitive unit cells will have 8 corner atoms. 8 corner atoms which will be shared by 8 unit cells. Like this you can write, or which will be shared by 7 other unit cells. Total it became 8 only. Okay? So you can write like this, which will be shared by 8 unit cells. Okay? So therefore, each unit cell, each primitive unit cell will have 8 into 1 by 8 is equal to 1 atom. Each unit cell will have 8 into 1 by 8 is equal to 1 atom. That should be the answer. So first 1 marks will be given whatever you have written, and another 1 marks will be given for your final answer. So that's how 2 marks will be distributed. All of you have understood? This one they have asked many times, not only primitive. All the unit cells, different types, whatever I have told, they have asked many times. But whether I am clear, and this is how you should write. So picture, don't waste your time in drawing the pictures. Not even primitive unit cell pictures are required. Okay? Just mention, calculate the number of atoms present in a primitive unit cell in a crystal lattice. Question, 2 marks question. Then you should tell that in a primitive unit cell it will have 8 corner atoms which will be shared by 8 unit cells, or which will be shared by 7 other unit cells. So this unit cell and 7 other, total it will be 8 only. So second point, it should be therefore each primitive unit cell in a crystal lattice will have 8 into 1 by 8 is equal to 1 atom. Whether I am clear? So 2 marks will be given to you if you have written like this. Some people, they will not write like this. They will remove this. They are in a hurry, right? Only this much, and they think that they should get 2 marks. I will not give 2 marks. I will give only 1 mark. Who knows? You might have by-hearted. You by-hearted that 8 into 1 by 8 is equal to 1, that is for primitive unit cell. And you might have written, then why should give 1 mark, 2 marks to you? So, board exam explanation is required. Okay? So that's where we have the 1 atom in a primitive unit cell. And we will come to next one. Oh, I didn't have it. Okay, let it be here. I will come to next one, centered unit cell. So I will go for body centered unit cell. I will go for body centered unit cell. So I will take any one of this. Okay. I will take the last box, and in the center of the box there will be presence of one atom. Along with the corner atoms, there will be presence of one atom in the center of the box. Now can you tell me, an atom which is present in the center of the box, whether it will be shared by any other unit cells? It's just like, now Raghavendra sir is taking the class inside this room, whether another room is also I am standing? No, I will belong to only this room. Same way, when I am talking about an atom present inside the cube, that atom completely belongs to that unit cell only. Right? It cannot be shared by any other unit cells. Just like a cricket ball which is present inside the box. Yes, Amit, it cannot be shared. So therefore, when it comes to body centered, unit cell, you should tell that it has 8 corner atoms shared by 8 unit cells. Therefore, 8 into 1 by 8 is equal to 1 atom. Then you should tell that it has one body or one atom at the center of the body. At the center of the body, which will not be shared by, therefore it will be equal to 1 atom. Total, it will be, total atoms is equal to 2 atoms or 2 elements. Right? So body centered will be having total 2 atoms or 2 elements in its unit cell, in a crystal lattice. All of you have understood? So that's where we have the body centered unit cell, calculating the number of atoms in a body centered unit cell. Each one has to be written. Don't simply write 8 into 1 by 8 is equal to 1 atom, and then don't write that in the center of the body 1 atom, total 2 atoms. This one fine, but here you should tell why 8 into 1 by 8. You should tell that one. You should give the reason. That is because that will be shared by 8 unit cells. Therefore 8 into 1 by 8. Okay? So that is related to body centered unit cells. That is related to body centered unit cells. Now we will move to the next one. That is face center. That is face center. Now what I will do is, I will go for last one. Upper one I will go. Okay? So along with the corner, I have atoms present on the center of each face. Okay, atoms present in the center of each face. So 1, 2, 3, 4, 5, and now, okay, here one should come. 6, that is back side face. So we have total 6 atoms present on each of the face. Altogether 6 is there. Now you should tell me, an atom which is present in the center of the face, whether it will be shared. So whether it will be shared? Yes, it will be shared. For example, imagine you have a room and you have a large iron nail, and you have made that iron nail to insert it into wall. One edge will be facing your room, on the other edge it will be facing the another room. That means that nail is common for your room also, neighboring room also, right? So we cannot have such a large nail, but you should imagine. Okay? So the same logic is applicable here. We have atoms on the center of the face, and face centered atoms will be shared by, okay, Purnima, no, it will be shared by only 2 unit cells. not 5. So imagine we have one unit cell. Okay, imagine we have one unit cell. Then I will draw another one. Only 2 I will draw here. Okay, so imagine we have the 2 neighboring unit cells, and in the center of the face we have 1. Okay, the same way we have on the other faces also. We'll focus on this one. Now can you imagine this unit cell belongs to here also, it belongs to here also. Now got the point, Purnima? Have you understood? Fine? Oh, you have written S. I thought you have written 5. Okay, fine. So that's where we have the atoms present in the center of the face, which will be shared by this unit cell also, this unit cell also. So therefore, a face-centered atoms will be shared by total 2 unit cells. A face-centered atoms will be shared by total 2 unit cells. Fine? So along with that, corner atoms will be there. Okay? So therefore, we have to give the explanation. So it will be having 8 corner atoms. 8 corner atoms which will be shared by 8 unit cells, Therefore, 8 into 1 by 8 is equal to 1 atom. Then each face has 1 atom which will be shared by 2 unit cells. Therefore, how many faces are there? Total we have 6. So 6 atoms. Total 6 atoms. 6 into 1 by 2 is equal to 3 atoms. So therefore, total atoms will be 3 plus 1 is equal to 4 atoms with respect to face-centered units. Fine? So that's how it should be written. All of you have understood? Why 6 divided by 2? 6 divided by 2 because each 6 face-centered atoms will be shared by 2 unit cells. Therefore, 6 divided